Destroyer Squadron 11 was a primary operational asset of the Pacific Fleet. In a matter of minutes, a sequence of precise navigational failures transformed an intact combat formation into an unrecognizable wall of shattered steel. In the end, what remained of 7 modern warships would be sold off as scrap for just $1,035. The collapse of the squadron was not caused by enemy fire or catastrophic mechanical failure. The disaster was initiated by an unwavering trust in a legacy method. The navigational reliance on dead reckoning, paired with deep skepticism toward early radio direction, finding bearings that suggested something was wrong, set a trap that would trigger a devastating high-speed chain reaction. The formation was executing a high-speed engineering endurance run. The destroyers were pushing a sustained 20 knots through heavy blinding fog along the California coast. Navigational visibility was reduced to absolute zero. By the early 1920s, radio direction finding could provide a usable radio bearing even through fog, but it was still primitive and a single bearing could be misread as its 180-degree reciprocal. On the lead ship, the RDF bearings placed the column farther east than the dead reckoning plot. Watson and his navigator discounted the warning and held the charted track, unaware that the set-off point Pedernales was sliding the formation sideways into danger. Convinced that the squadron had safely cleared the critical turning point at Point Arguello, the command vessel ordered a sudden 95-degree turn at about 2100. This aggressive maneuver was meant to bring the fast-moving formation into the Santa Barbara Channel. With no moon, heavy fog, and the RDF warnings dismissed, the charted position was wrong, and the 95-degree turn drove the column straight toward Honda Point, the Devil's Jaw. Within minutes of putting her rudder over, the lead destroyer slammed into the rocks, careening broadside and breaking in two. The violence of a 20-knot ship meeting volcanic stone shredded steel in seconds. The training plan held the column in a tight single file, a Form 18, with the bow of each ship roughly 150 yards from the stern of the one ahead. The destroyers followed the flagship's movements by wake and instinct. In a tight Form 18 with roughly 150 yards between ships at 20 knots, where the next captain had only seconds, S.P. Lee swung hard and still found rock. Young was ripped open, flooded fast, and rolled over. The rest of the line discovered the trap at the last moment. In rapid succession, more destroyers piled into the same rocks. Some sheared away in the last moments and 2 managed to extricate themselves. But 7 ships, half the squadron, ended up wrecked and pinned by surf and stone. 23 sailors died during the rapid sequence of impacts and breakups. 3 of those deaths occurred as the lead ship, the USS Delphi, broke apart and her aftersection went under. The most severe single loss came aboard the USS Young. Submerged rock tore into her hull, water rushed in, and the ship capsized with brutal speed. In that sudden roll, 20 of the 23 fatalities were lost inside Young's overturned hull. Dawn revealed a continuous, mangled wreck field of 7 premier warships driven deeply onto the rocks. The operational command structure had catastrophically failed. The engineering problem immediately transferred from fleet navigation to emergency recovery. Naval architects now faced the brutal task of extracting high-value military assets from an overlapping wreckage field. A conventional recovery operation inherently assumes that a compromised ship rests in deep water or floats freely on a forgiving surface. These wrecks were jammed into a violent, zero-depth surf margin where floating cranes could not approach, forcing salvage planners to treat the field as a single, interlocked mass of steel. On September 11, 1923, our naval constructor, Captain D.C. Nutting, arrived on the remote coastline to survey the twisted steel labyrinth. A Clemson-class destroyer displaced roughly 1,200 tons in standard condition, a compact mass of steel, boilers, turbines, and wiring. These vessels were originally engineered strictly for high-speed velocity and rapid maneuverability. To achieve superior combat speeds, naval architects designed them with relatively thin outer hull plating. This optimized combat geometry made them exceptionally vulnerable to blunt force trauma. Nutting had to evaluate if any of that heavily compromised tonnage could be safely refloated and towed back to a naval shipyard. The assessment required a strict analysis of coastal fluid dynamics. The surf zone is the most hydraulically violent marine environment on the planet. When deep ocean swells impact shallow coastal shelves, the continuous kinetic energy does not dissipate gradually. It is forced violently upward and forward, creating an endless cycle of massive hydraulic battering. Ships grounded in an active breaker line never rest statically. Every incoming Pacific wave lifts, twists, and forcefully drops the massive steel structures against the unyielding stone pinnacles below. The ocean operates as a continuous industrial grinding machine. This relentless flexing rapidly destroys structural integrity along the main keel line. The continuous kinetic energy literally pulverizes thin military hulls against the solid underwater reef structures. Nutting observed the severe tearing and the nonstop pounding of the surf line. His report made a hard distinction. Most of the wrecks were beyond practical recovery as intact ships, and salvage as a whole was considered impracticable in that breaker zone. Yet he also noted that one hull offered the best chance, at least in theory, for being worked free under the right conditions. With time and weather working against them, the immediate mandate shifted to stripping what could be safely reached, radios, instruments, and heavy deck gear above the crushed lower sections, before the sea finished the job. With floating cranes unable to come alongside, crews built sheer legs, 2 massive timbers lashed into a rigid A-frame on the most stable surviving deckhouses and reinforced roofs. From these improvised frames, for block and tackle and hand winches, hoisted the 4-inch guns clear of their mounts before the surf could wrench them away. The massive steel weapons were safely suspended in the air above the ruined destroyers. But lifting the guns clear was only step one. They still had to be hauled across the churning gap and up to solid ground, which meant a highline anchored on shore and powered from land. Moving suspended industrial tonnage across an unstable gap requires a rigid suspension cable and a continuous terrestrial anchor. The physical environment off the California coast offered absolutely no stable platforms on the ocean side. The singular geometric advantage existed strictly on the adjacent mainland. Directly overlooking the twisted steel labyrinth, jagged earthen bluffs rose dramatically to an absolute elevation of 50 feet. The Naval Salvage Command recognized this vertical dominance as the only viable foundation for a continuous extraction chain. Lieutenant C.F. Osborne directed the immediate construction of a centralized operational encampment directly atop the cliff edge. This elevated staging ground would serve as the primary anchor point for a massive highline hauling network. Establishing a highline system demands perfect tension geometry. Heavy steel cables were manually dragged from the bluff down to the stranded vessels. The lines were secured tightly between the shipboard rigging and massive anchor posts driven deeply into the dense coastal rock above. The steep vertical drop from the bluff to the ships provided a natural upward angle for the extraction path. However, suspending thousands of pounds of concentrated weight on a long cable span inevitably causes severe midline sag. To prevent the heavy payloads from dipping dangerously into the gap during transit, the main cables had to be drawn to maximum tension. Generating the necessary brute pulling force to achieve this extreme tension and continuously haul the massive payloads up the steep incline became the central engineering crisis. With no shipboard machinery available on the bluff, the pull had to come from ashore, steady, sustained traction from whatever engines and animals could be assembled on the plateau. That shore power then had to be matched precisely to the riggers working far below. Operating without electronic communication devices, the teams relied on strict visual signaling to synchronize the massive transfer of weight. Complex block and tackle assemblies were lashed firmly to the thick steel hitches of the diesel tractors and the heavy leather harnesses of the draft animals. The extraction cycle operated on a brutal, continuous rhythm. Once the maritime crews successfully secured a heavy military payload to the lower traveler block of the highline system, a designated flagman visually relayed the exact extraction command to the cliff edge operators. The tractor drivers and teamsters instantly engaged their respective power sources and drove straight inland. They moved steadily away from the precipice, driving in a straight, unyielding path parallel to the flat ground of the bluff. This continuous terrestrial forward motion translated instantly into sheer diagonal pulling force along the main suspended cables. The relentless towing power of the motorized tractors and the biological muscle of the horse teams dragged the massive naval hardware relentlessly upward. The synchronized pulling effort smoothly erased the dangerous sag in the heavy wire rope, and pulled the swinging steel components securely up the sheer face of the 50-foot cliff. The brilliant geometric arrangement successfully converted horizontal agricultural towing momentum directly into extreme vertical maritime extraction force. As each heavy payload breached the crest of the bluff, the cliffside crews carefully slacked the lines, lowering the recovered military assets safely into the staging camp. This primitive but highly effective industrial pipeline successfully bypassed the severe lack of naval heavy lift infrastructure. The continuous cyclic rhythm of securing, signaling, and hauling salvaged crucial operational equipment at a rapid pace. The operation successfully stripped the most accessible and valuable external assets from the stranded vessels. Yet the relentless extraction pace was fundamentally dictated by the physical state of the underlying hulls. As the highline operations continued from the bluff, the lower sections of the outermost wreckages began to settle much deeper into the coastal trench. The slow downward shift of the massive steel bodies introduced an entirely new and intensely lethal complication. A heavily localized secondary explosive hazard began to sink permanently beneath the waterline. A fully armed combat destroyer was engineered to deliver devastating broadside attacks using multiple 21-inch torpedoes. These weapons were immense, the highly complex machines packed densely with extremely sensitive high explosives. While heavy deck armaments like the main guns could be forcibly unbolted and hoisted upward, extracting the heavy torpedoes presented a totally unacceptable level of volatility. The heavy steel mounts containing the live weapons were severely warped by the massive kinetic trauma of the initial coastal grounding. The precise internal geometry of a torpedo tube leaves virtually zero clearance for the weapon inside. Because the outer steel tubes were now physically bent and crushed, the live torpedoes were tightly wedged into the metal casings. The immense weight of a 21-inch torpedo dictated that any physical extraction would require tremendous pulling force. Dragging a delicate, explosive cylinder out of a bent, the heavily damaged steel tube using crude mechanical tension would generate immense metal friction. The salvage engineers recognized that this force-scraping action could easily crush the delicate internal firing mechanisms. A single structural spark or sharp mechanical shock during a forced hoist would instantly trigger a massive close-quarters detonation, vaporizing the adjacent salvage teams and destroying the surrounding wreckage. As the seaward wrecks settled, their torpedo tubes went under, leaving live weapons trapped in crushed mounts beneath the surf. It was a deadlock, too dangerous to pull them free, and too dangerous to leave that explosive mass to be worked and detonated by the rocks. To break this deadlock, the Salvage Command turned to an unconventional solution already written into the tubes themselves. Rather than trying to wrench torpedoes out of bent mounts, salvage logs report that several torpedoes were fired out to sea from the wrecks, including 3 from Young and 1 from Woodbury, using the torpedo tube's normal expulsion system. It was a drastic measure taken to reduce the immediate danger of live weapons trapped in crushed steel. Other ammunition, however, still remained on board at that stage, and the surf zone stayed lethal long after the torpedoes were gone. This brilliant in situ clearing maneuver successfully neutralized the explosive threat without requiring a single highly unstable weapon to be lifted through the air. The radical neutralization removed the final critical operational hazard from the immediate site. However, the systematic stripping phase was rapidly running completely out of time. The broader Pacific environment was aggressively shifting, signaling the definitive and permanent closing of the safe operational weather window. On this exposed stretch of the California coastline, the late summer weather window was closing fast as autumn swells began to build. The naval teams had pushed their temporary extraction networks to the absolute physical limit. As the Pacific swells steadily increased in height and frequency, the remaining heavy machinery on the outermost wrecks became completely inaccessible. The water surge across the broken main decks was now continuous and highly lethal. Sending human riggers out to secure heavy lift cables directly into the crashing white water was mathematically unjustifiable. The operational command evaluated the rising wave data and made a final structural determination. They officially declared that the deepest heavy items and the outermost structural assets would be permanently abandoned due to extreme surf danger. By late September 1923, the Navy's on-scene stripping work had reached its practical limit. Responsibility for the remaining hulks shifted toward commercial salvage, including the Merritt, Chapman, and Scott Company, whose aim was to cut down the wrecks and recover machinery where the sea would allow. However, no amount of experience could negotiate with the seasonal shift. As winter swells arrived, access windows vanished. Wave after wave worked the wrecks loose, buckled what remained above water, and broke sections apart faster than crews could cut them down. The commercial teams realized that any systematic teardown was being overtaken, and in places erased by the sea itself. The response ended in partial success. Naval crews stripped what they could reach, recovered key guns and instruments, and reduced the immediate ordnance danger. But deeper structural salvage failed as winter seas arrived, and Merritt, Chapman, and Scott ultimately withdrew, leaving the lower hulls to the surf. The once proud combat formation became a jagged underwater debris field, and the remaining hulks were sold off as scrap. With the shoreline now beyond recovery, the focus shifted inland, to a legal arena tasked with assigning responsibility for the navigational failure. After a failure of this scale, institutions often spread blame to shield the top. The Navy convened a sweeping tribunal to account for the loss of combat capability, built to interrogate each decision in the chain. For the surviving officers, the move from surf-torn wreckage to a sterile courtroom became a second ordeal. The tactical doctrine of the era placed the subordinate ship captains in an impossible professional trap. The established military doctrine demanded absolute, immediate compliance with the speed and heading of the command ship. In practice, that meant matching the command ship's speed and turns without independent confirmation. Breaking formation without a direct, verified order was considered a severe violation of strict naval protocol. Therefore, the captains of the trailing destroyers drove their ships directly onto the unyielding coastal rocks specifically because they were executing their foundational military duties flawlessly. Despite their strict and proper adherence to operational doctrine, the sweeping, institutional investigation possessed the legal power to terminate the careers of every captain involved simply because their massive steel vessels were destroyed. Commodore Watson possessed a profound understanding of this looming institutional threat. As the highest-ranking officer on the bridge of the lead ship, he held the supreme operational authority over the entire formation. He also possessed the rank and the institutional leverage to argue that unpredictable ocean currents or inherently flawed atmospheric conditions caused the disaster. He could have easily deflected a significant portion of the ultimate blame downward, citing the individual operational responsibility of each ship captain to navigate their own vessel safely regardless of the squadron alignment. He could have subjected his junior officers to grueling cross-examinations and endless professional scrutiny. Instead, Watson stood directly before the stern assembly of high-ranking admirals and executed a deliberate, definitive legal maneuver. He formally and absolutely assumed full, unmitigated responsibility for the entire coastal catastrophe. Before the court, Watson stated that the navigational failure and the fatal turn were his alone, deliberately shielding his subordinate captains from career-ending blame. This deliberate assumption of total guilt was an act of extreme professional sacrifice. The court-martial tribunal legally stripped him of his accumulated seniority and permanently ended his upward trajectory within the naval command structure. He knowingly traded his own highly prestigious career and his personal historical legacy to ensure that the junior officers who blindly followed his orders into the thick fog would not be unjustly punished for their strict military loyalty. In that courtroom, Watson accepted the failure as a consequence of his own command decisions and paid the price. The ships were lost to the Pacific, but the principle of command responsibility endured.